I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine if the next generation of armor, drones, or hypersonic aircraft could be designed not in decades, but in months. That's no longer science fiction. It's what happens when artificial intelligence and machine learning take command of material discovery, redefining how militaries build strength, speed, and survivability. In the race for defense superiority, materials are the hidden enablers of power. They define how light a fighter jet can be, how long a battery lasts in the field, and how much heat a missile can withstand at Mach 5. From advanced composites to self-healing coatings and ultra-efficient semiconductors, every breakthrough in defense hardware begins with a breakthrough in materials science. Traditionally, discovering those materials took years of trial and error. Scientists would experiment endlessly, mixing metals, ceramics, or polymers, hoping to stumble on something that worked. But warfighters can't wait for eureka moments. In an era of rapid technological change, slow discovery means strategic vulnerability. That's where AI is transforming the battlefield before a single weapon is built. Machine learning can now analyze massive data sets of chemical and physical properties to predict which combinations will yield lighter armor, tougher alloys, or more heat-resistant composites. It's like having a digital lab that runs millions of experiments in hours, revealing which materials will perform best long before they're ever made. For instance, Google DeepMind recently discovered more than 2.2 million new materials, with nearly 400,000 predicted to be stable enough for real-world use, compressing decades of discovery into a single digital leap. Many of these could lead to better batteries, lighter vehicles, and more efficient electronics for both civilian and military systems. In defense research, DARPA is backing pioneering initiatives such as the Autonomous Research System (ARIS) program, an effort to develop fully automated self-driving laboratories that can autonomously mix, test, and optimize materials 24/7. These AI-powered systems don't replace scientists, they amplify them, accelerating the feedback loop between hypothesis, testing, and battlefield deployment. The U.S. Army's collaboration with SandboxAQ, an Alphabet spinoff, is already applying AI to create lighter, stronger alloys for armored vehicles and to design next-generation batteries for drones and soldier systems. Similarly, Cornell University's Crystal system used machine learning to discover a new methanol fuel catalyst that could power soldiers' portable energy devices more efficiently. In China, AI-assisted catalyst discovery recently shrank a 35-year research task into just 6 months, underscoring how global this technological race has become. To understand how it works, think of machine learning as a predictive microscope. It looks at the atomic structure of materials and forecasts how they'll behave under extreme stress, temperature, or radiation. This means scientists can model a new alloy's performance in hypersonic flight, or simulate how a ceramic armor would absorb a blast without ever building a prototype. And real results are emerging fast. Ultralight metal glass hybrids developed at Northwestern University through AI optimization now offer armor-grade strength at a fraction of the weight. At Argonne National Laboratory, AI predicted the thermal behavior of a new 2D material called stannane, ideal for high-speed electronics and radiation-hardened spacecraft. And at Los Alamos, adaptive machine learning models have guided experiments towards self-healing ceramics, which can repair microcracks caused by battlefield stress, extending the life of critical components. The potential impact is enormous. Tanks that move faster, aircraft that fly higher, drones that last longer, and soldiers who carry less weight into combat, all driven by smarter, faster material design. But while AI accelerates innovation, it also introduces a new dimension of strategic risk. The same algorithms that design advanced armor or stealth composites could be exploited to engineer corrosive compounds that degrade enemy systems, develop nanomaterials that disrupt radar sensors, or create alloys with built-in weaknesses that trigger failure after repeated use. Weaponized materials like these could quietly cripple logistics chains, sabotage production lines, or erode combat readiness, turning material science itself into a new front of hybrid warfare. That's why securing AI models, datasets, and design pipelines is now as critical as securing the materials they create. Organizations like NATO's Emerging Technology Security Framework are working to set guardrails so that innovation strengthens security rather than undermines it. One thing is clear. The nations that master AI-driven materials discovery will command the technological edge of the future battlefield. Because tomorrow's power won't be forged only in steel or silicon. It will be discovered in data, designed by algorithms, and printed in the field. The race is on, and AI is the new forge of defense innovation.
Thanks for watching. Subscribe, follow, or visit IDSTH.com for more cutting-edge defense and tech insights. See you in the next one.